Bicycle has two wheels. Bisector will divide something into two parts. So in this topic, binomial expansion, we are going to be working on two terms, and we're going to discuss how two terms, when it is to the power of n, can be expanded using this formula here. And at a glance, I believe this formula looks so intimidating, but please be assured, after a while you realize that this formula is actually very, very easily applied. In fact, this formula can also be found inside your formula sheet. Let me show you where it is. On your formula sheet, you can actually find it here under binomial expansion. Exactly the formula that I have on the board here. And this formula is for n being positive integer, which is what I wrote here also. So the power must be to the power of 1, to the power of 2, to the power of 3, and so on. And there's this thing here. Okay, a further definition from the terms that is in the expansion. This thing, it is pronounced as n choose r. So for what we have here, this is called n choose 1, and this is called n choose 2. And for n choose r has a further definition. For n choose r, according to what we can see in our formula sheet, this is described as n exclamation mark divided by r exclamation mark, then n minus r exclamation mark. And this sounds bad. Okay, this sounds bad because no one will be pronouncing this as exclamation mark in math. This is called the factorial notation. In fact, we can find this factorial notation on our calculator. It is here, the factorial notation. Let me give you an example. Let's say we have a 7 choose 5. So according to this definition, it is going to be 7 factorial divided by 5 factorial, then 7 minus 5 factorial. So this is 7 factorial divided by 5 factorial, and 7 minus 5 is 2, so 2 factorial. So for 7 factorial, we can just simply press it into our calculator, 7 factorial. That gives me a 5040. So here we have a 5040 divided by 5 factorial. 5 factorial, 5 factorial. This is 120. So here is 120. And then 2 factorial. 2 factorial is, let's check, 2 factorial. This is equal to 2. So what exactly is this factorial? I can also further define this for you, okay? It is like really very simple also. So for this 7 factorial here, 7 factorial, okay, I mean, of course, we can press it in our calculator, we get a 5040. But 7 factorial is actually just 7 times 6 times 5 times 4 times 3 times 2 times 1. And 5 factorial, yes, it is 120. It is also 5 times 4 times 3 times 2 times 1. Yes, factorial will always go back to 1, which means that 2 factorial is going to be 2 times 1, which means that 9 factorial is going to be 9 times 8 times 7 times 6 times all the way until 3 times 2 times 1. It will always go back to 1. Should we just press this in our calculator to check what is 7 choose 5? Yes, we can. But at the same time, our calculator also gives us a means to just directly calculate 7 choose 5 by making use of this. So if we were to press 7 choose 5, we can immediately get the result. This is equal to 21. There's another formula that is defined for us in our formula sheet. It is this over here. So this defines n choose r as n times n minus 1 and all the way until n minus r plus 1 divided by r factorial. Which means that if I were to apply it to this, the denominator is going to be r factorial. So the denominator is going to be 5 factorial. This is easy. For the numerator, it's going to start with a 7. Then after that, 7 minus 1. Then all the way until 7 minus 5 plus 1. 7 minus 5 is 2, plus 1 is 3. So all the way until 3. This formula actually looks very difficult to, it feels very difficult to memorize, but it's actually very, very easy because it actually follows a certain format. If I were to just write down all the terms in the numerator, it's going to be 7 times 6, then 5, 4, 3, divided by 5 factorial. So what you will realize is that when it is going to be 5, in the numerator, there will be 5 terms. 7, 5, 7, 6, 5, 4, 3. 5 terms. So if I were to have a 10 choose 3, here is going to be 3 factorial, and in the numerator, I'll be expecting 3 terms. So I'll just write down the 3 terms. 10, 9, 8. Although, we can also see this 8 as 10 minus 3, 7 plus 1, which is equal to 8. But I think, personally for myself, it is easier for me to see 3 and then 3 terms. 5, and then I will just write down 5 terms. Of course, you may think that why not we just press the calculator all the way? But today, we are going to look at some examples, and I'll show you that this formula here is actually pretty useful for us to solve a particular kind of question in binomial expansion. Okay, but that will be the question I'm going to be doing last today. So, for what we have here, let's try to do an expansion, shall we? Let's try to apply it to a very simple scenario. How about let's go for something that we can already expand, like for example, a 3 plus x to the power of 2. Every one of us know how to expand this, right? 3 plus x to the power of 2. And what is this? This is going to be equal to 3 square plus 2 times of 3x plus x squared. So we are expecting this to be a 9 plus 6x plus x squared. Let's see whether binomial expansion works, since it's meant to expand 2 terms to the power of n, and n is a positive integer. So we have all the condition that is necessary here in order for us to apply the binomial expansion. So the first term is going to be equal to a to the power of n. If we were to just match this to what we have here, okay, you can see that a is equal to 3, b is equal to x, and n is equal to 2, right? You guys can see this, right? So we have a to the power of n, so it's going to be 3 to the power of 2, then plus 2 choose 1, which you can press it into a calculator. Then according to what we have here, it's going to be 3 to the power of 2 minus 1. Then we have b, which is x. So I'm going to write down the next term. So how many terms should we be having? It is actually very, very easy. You know why? Because when it is to the power of n, I will actually be expecting n plus 1 number of terms, which means that if it is to the power of 2, I will be expecting 2 plus 1, 3 terms. So there will be just one last term. So for this last term, it is going to be b to the power of n. So it's going to be equal to, here it will be a x to the power of n, which is 2. Let me explain to you why we are expecting 3 terms when it is to the power of 2. Why are we expecting n plus 1 number of terms when it is to the power of n? Because in the formula that we are learning now, it actually removes some coefficients which are pretty consistent. For example, right, this is not just simply a to the power of n. The very original form of the first term here is actually n choose 0, then a to the power of n minus 0, then b to the power of 0. Because every term looks like this. N choose r, a to the power of n minus r, b to the power of r. So the very first term will be n choose 0, a to the power of n minus 0, b to the power of 0. Then the next term will be n choose 1, a to the power of n minus 1, b to the power of 1. N choose 2, a to the power of n minus 2, b to the power of 2. So there is a pattern that is going on. And for n choose 0, the reason why it has been missing from here is because n choose 0 is always going to be equal to 1. Not a proof, but I can just show you using some numerical calculation. For example, let's use our calculator, okay? What if we were to do a 7 choose 0? So 7 choose 0. What do we get? 1. Just like what I was saying. Let me give you another example. Let's say we have a 15. So what if we were to do a 15 choose 0? It is equal to 1. That is why n choose 0 is always going to be equal to 1. That is why it is missing from here. And minus 0 is still going to be equal to n, right? So it is just simply written as a to the power of n. And b to the power of 0 is always going to be equal to 1. So again, it will just disappear. That's why the first term looks like just a to the power of n, but it actually has more terms that is being attached to it. So if it is n choose 0, n choose 1, n choose 2, then all the way until this. This is again b to the power of n, which there are also other terms that are attached to it. Other terms that are attached to this very last term here is actually n choose n, a to the power of n minus n, then b to the power of n. I'm hoping that you guys can see the pattern because every single term is actually pretty consistent. 1, 1, 1. So if this is n, then you'll be n, n, n. And n choose n is also always going to be equal to 1. Let me justify this for you using this. Okay, let's say we have a 12 choose 12. It is going to be equal to, whoops, let me just press it again. 12 choose 12. So 12 choose 12 is equal to 1. Let me give you another example. Let's say 6 choose 6. This is also going to be equal to 1. So n choose n is always going to be equal to 1. And that is why this term will disappear. A to the power of n minus n is going to be a to the power of 0. It's also going to be equal to 1. So this will be 1, this will be 1. You will be just left with b to the power of n. And if you were to now count 0, 1, 2, 3, 4, 5, all the way until n, how many terms do you think there will be? There will be n plus 1 number of terms. So that is how I know when I try to apply this formula, how many terms should I be writing before everything is going to stop. So to the power of 2, we are going to be expecting 3 terms. And let's evaluate this. So this is going to be 3 to the power of 3 plus 2 choose 1. Let's press it into our calculator. 2 choose 1, 2. Then we have a 2. So 2 choose 1. 2 choose 1 is equal to 2. So here we have a 2 of 3 to the power of 1, then x plus x squared, which gives us a 9 plus 6x plus x to the power of 2. It is exactly the same as this. So now let me try to show you a few more examples, a few more scenarios, how binomial expansion is going to be tested in your, to show you some common ways that binomial expansion is going to be tested. And I believe that through that, you will probably be able to apply this formula pretty well because it is really, okay, trust me, it is really not a very difficult formula to apply. So let me erase this. Okay, and let me erase this small little one that is over here. So we are retaining the same formula as what we have inside our formula sheet. The first scenario, the first common scenario that you will be seeing this being tested in an exam is literally the expansion. So let's try to see how we can do an expansion for this. Okay, let's try to expand this. This 3 minus 2x to the power of 5. So we're going to try to use the binomial expansion formula. How many terms will we be expecting? We will be expecting 6 terms. Okay, 5 plus 1, so we'll be expecting 6 terms. The first term is going to be 3 to the power of 5. Then plus, the next term will be 5 choose 1. Then 3 to the power of 5 minus 1, which is going to be 4. Then the second term to the power of 1. Then the next one is going to be 5 choose 2. Then 3 to the power of 5 minus 2, which is 3. Then minus 2x to the power of 2. Then after that, we have a 5 choose 3. Then 3 to the power of 5 minus 3 is 2. Then minus 2x to the power of 3. Then 5 choose 4. 3 to the power of 5 minus 4, which is 1. Then minus 2x to the power of 4. And we will have the last term already, right? Because I have 1, 2, 3, 4, 5. So there are only 6 terms. So the last term is going to be minus 2x to the power of n, which is 5 in this case. It is this. So let me evaluate this. 3 to the power of 5. This is equal to 2, 4, 3. And 5 choose 1, 3 to the power of 4 multiplied by minus 2. I'll just press this in the calculator. We will be getting this as minus 810x. Similarly, if I were to just press this in our calculator, we'll be getting a plus 1080x squared. Then negative 720x to the power of 3. Then plus 240x to the power of 4 and minus 32x to the power of 5. I've missed out some details as I try to describe to you guys about this question, which is, this question is asking us, can we try to expand this in ascending powers of x? So is this in ascending powers of x? Yes, it is. because it is going to be x to the power of 0, x to the power of 1, 2, 3, 4, 5. It is in ascending powers of x. But what if the question were to ask me, can you try to expand this, but in descending powers of x? Of course, we can expand the entire, we can get the entire expansion, then we reverse this entire expansion. So I'm going to start by writing this as a first term. Okay, that is something that we definitely can do. But what if we were to try to make use of this formula and do the expansion directly, but it will immediately be in descending powers of x? Can this happen? If we are given this 3 minus 2x to the power of 5, and we are supposed to expand this in descending powers of x. Okay, we are going to try to see a pattern. I need you to try to focus about this together with me, okay? So if you were to look at expansion, do you realize that for the first term, the power is constantly decreasing? It is not about the position of x, okay? It is about the first term and the second term. And the second term, the power is increasing, right? To the power of minus 2x to the power of 0, to the power of 1, to the power of 2, to the power of 3, to the power of 4, and then to the power of 5. Which means that whatever that you place in the first term, the power will just keep decreasing. Whatever that you place in the second term, the power will just keep increasing. So if we want to expand this in decreasing powers of x, we're going to place x, the term that is multiplied to x. We're going to place that term as the first term. Because for the first term, the power will just keep decreasing and decreasing and decreasing. Which means that if I were to expand this in decreasing powers of x, another strategy that I can make use of is to just switch the first term and the second term so that x is at the first term. Then when I apply the binomial expansion, this is going to be minus 2x to the power of 5, then plus 5 choose 1, then minus 2x to the power of 4, 5 minus 1 is 4, then 3 to the power of 1, then 5 choose 2, minus 2x to the power of 3, 3 to the power of 2, 5 choose 3, minus 2x to the power of 2, then 3 to the power of 3. Then after that we have a 5 choose 4, minus 2x to the power of 1, then 3 to the power of 4, and the last term is going to be 3 to the power of 5. And if I were to evaluate this will actually synchronize to this term over here. So this is going to be equal to minus 32x to the power of 5. Then we have a plus 240 x to the power of 4 minus 720 x to the power of 3, then plus 1080 x to the power of 2 minus 810 x, then plus 243. And now it is going to be in descending powers of x. Power 5, 4, 3, 2, 1, 0. Expansion in ascending or descending powers of x can be very easily achieved using the binomial expansion depending on where you are going to be positioning your x. So expansion, definitely it is one of the most common way that binomial expansion is going to be tested in the exam. Let me show you the second common way that this is going to be tested, and that is when we are supposed to be extracting certain term from the binomial expansion. To extract certain term from the binomial expansion, we are going to look at the expansion formula once again. And in the expansion formula, I want to look at the more general term. And it is also inside our mathematical formula that the general term is going to look like this. N choose R. A to the power of n minus R, B to the power of R. If I were to look at this, and I'm going to name this as the first term, and the notation I'm going to make use of is to call this T1. This is the second term, this is T2. This is the third term, this is T3. If the same notation continues, can you deduce this is T what? Can you deduce this? Let's look at what we have again, okay? So T1, okay, this is T2, it is n choose 1, 1, 1. T3, this is 2, 2, 2. So if this is R, 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 this should be TR plus 1. Can you see it? Right? Because T2, then this is 1, 1, 1. It is minus 1. T3, the third term, this is 2, 2, 2. So if this is TR plus 1, this will be R, R, R. So the general expression for the individual term that is in the binomial expansion is going to be this, the TR plus 1 term. Okay, it is a bit confusing. Maybe some of us need a little bit more time to internalize this. So let's take a few seconds to think about it. Okay, TR plus 1 is n choose R, a to the power of n minus R, b to the power of R. Okay, it requires a bit of time to get used to. But let me just show you a few examples, and hopefully it will get us more and more used to the fact that we are looking at a TR plus 1 term. For example, if we have this 3x minus 5 to the power of 7, and we want to extract out the fourth term. The fourth term means the T4 term, right? T1, T2. T1 means the first term. T2 means the second term. So the fourth term is T4. And 4 is like 3 plus 1, which means that for the fourth term, R is equal to 3, TR plus 1. So this is going to be equal to, if I were to make use of this, is going to be n, which is 7, choose R, which is 3, and choose R. Then A, which is going to be 3x here, to the power of n minus R. Then B, which is minus 5 to the power of R. So this is just immediately going to be giving us the fourth term, T4. And this 7 choose 3, I'll just press it into the calculator. 3 to the power of 4, then multiply by minus 5 to the power of 3. That gives me a coefficient of minus 354,375. Then we have a x to the power of 4. Let me show you another example. Let's say we have this. We are now given this x minus 2 over x to the power of 3. And we have to the power of 16. Okay, just a very quick question. For this, how many terms are we going to be expecting? 16 plus 1. So we're going to be expecting 17 terms. Okay, we're not going to expand this. We're just going to be looking at some terms. It is going to be the term that is x to the power of 8 for part A. Can we try to find the term that is x to the power of 8? If we cannot have the skill to extract out certain terms, that means that to get the x to the power of 8 term, we need to expand all the 17 terms. We need to get all the 17 terms, okay? And that is going to be totally tedious. I am glad that we have just discussed about how we can extract out the TR plus 1 term. So for what is the general expression for the TR plus 1 term for this? It is going to be 16 choose R, then x to the power of 16 minus R, minus 2 over x cubed to the power of R. Let's try to simplify this, okay? This is going to be equal to 16 choose R, then minus 2 to the power of R. This is x to the power of 16 minus R, and this is going to be equal to x to the power of minus 3R. So I can consolidate this further. It will be 16 choose R, then minus 2 to the power of R, x to the power of 16 minus 4R. And now I'm ready to look at part A. Part A, we are looking at the term where the power of x is equal to 8. The power of x is equal to 8, which means that we are going to be letting the power of x, which is 16 minus 4R, be equal to 8. And for this, you're going to be getting R to be equal to 2. If R is equal to 2, what is the TR plus 1 term? We are talking about T2 plus 1, T3 terms. And T3 terms, when R is equal to 2, is 16 choose 2, then minus 2 to the power of R, which is 2, then x to the power of 16 minus 4 times R, it is 8 that we have found. So it is going to be to the power of 8. So this is going to be equal to 480, x to the power of 8. Done. Okay, we have found the T3 term, which is going to be the term that has x to the power of 8. What if the question wants the term that is independent of x, B? The term that is independent of x. We need to first understand what it means by independent of x, which means that x doesn't appear in the term. Is it possible that I have a term but x doesn't appear in the term, but yet we can discuss about x? Yes, we can. This will be the scenario where we are talking about x to the power of 0. It is the term that is independent of x, because x to the power of 0 is 1. So it sort of like disappear. So the term that is independent of x has the power equal to 0. So we're going to let 16 minus 4r be equal to 0. This will help me to find r. It is equal to 4. If r is equal to 4, that means we are talking about t4 plus 1, t5 term. And this is equal to 16 choose r is equal to 4. So 16 choose 4. Then minus 2 to the power of r, which is 4 in this case. Then x to the power of 16 minus 4 times 4, x to the power of 0. It is a term that is independent of x. And this, if I were to press it into the calculator, is 58240. Let me show you one more kind of question that you can possibly face in an exam. And this is on the second page of the outline. Let's take a look at this particular question over here. So for this binomial expansion, we are going to be looking at 1 plus px to the power of n, where n is a number that is bigger than 0, obviously, because in order for us to be applying this formula, we need to make sure that n is a positive integer. So n is going to be positive. And when this is being expanded in ascending powers, we are given this. X is in the second term, which means that if I were to be expanding this by itself, I'm also going to be getting an ascending powers. And since it's going to be matched to this, we are going to try to find the values of n. We are going to try to find the values of n, p, and q. Okay, let's try to find the values of n, p, and q. So to do this, what we are going to try do is, let's try to do an expansion for this, shall we? Let's try to expand this. And if I were to expand this, it is going to be 1 to the power of n, which is still going to be equal to 1 plus n choose 1. Then we have a 1 to the power of n minus 1, which is still going to be equal to 1. Then we have a px to the power of 1. It is this b over here. And the next term is going to be n choose 2. Then 1 to the power of n minus 2. Then px to the power of 2. We're going to expand it 3 times. Okay, I think I've already, I've done it 2 times here, okay, so I'm probably going to remove one expression here. So let's just refer to this, okay, let's just ignore this. This is probably a mistake. I'm going to remove it in the actual outline. So coming back to this, we have another term, right? Because we need an x to the power of 3. This is going to give us an x to the power of 2. So let me write down one more term. So the other term is going to be n choose 3. Then 1 to the power of n minus 3. Px to the power of 3. And all the rest of the terms, which I don't really care for this particular question. I just want my expansion all the way until x to the power of 3. So let's do a quick simplification to this. This is definitely going to be 1. How about n choose 1? N choose 1. I guess this is when we are going to try to make use of this. I was saying that this formula here is actually still pretty crucial, although many times we can press it into our calculator to evaluate. But the moment when we have a problem in evaluating, that is when we are going to be making use of this. And this is actually more useful than this. Okay, I find myself using this more. For example, what is n choose 1? N choose 1 is going to be, if I were to use this formula, right, it is going to be, the denominator is going to be 1 factorial. According to what we talked about just now, if the denominator is 1 factorial, then the numerator has only one term, which is going to be just n. So this is going to be equal to 1, and so this is going to be just px. So this is, the denominator is going to be 2 factorial. So the numerator will have 2 terms. The first term is going to be n. The next term is going to be 1 less than n. This is going to be 1. And this, we have a p square x square. As for this, the denominator is going to be 3 factorial. So the numerator will have 3 terms. Using that formula, it is going to be n minus 1. And the next term is going to be 1 less than this. So n minus 2. Okay, the first term is going to be n. The next term is going to be 1 less than this, so n minus 1. The next term will be 1 less than this, so n minus 1 minus 1 will give me n minus 2. Then we have 1 to the power of anything is still going to be equal to 1. And here is this. Then x to the power of 3, and so on. this is going to be 1 plus n divided by 1 factorial. 1 factorial is just 1. So it's going to be n px plus 2 factorial. 2 factorial, we can press this with our calculator, or it is just simply 2 times 1, which is going to be 2. So it's going to be n minus 1 p square over 2. Then this is going to be equal to x squared. Then plus this 3 factorial. 3 factorial is 3 times 2 times 1. So 3 times 2 times 1 is 6. So what we have here is going to be n minus 1, n minus 2. This is p to the power of 3 divided by 6. Then x to the power of 3, and so on. And now we can match what that is given to me to this that we have just derived. What that is given to me is this. Let's take a look at it again. It is 1 minus 12x plus 28 p square x square plus q x to the power of 3. So now if I were to just try to match the coefficient, I think I'm going to make use of this first. Okay, because this is x square, p square, which means that this n minus 1 divided by 2, this should be equal to 28, correct? Okay, I'm matching this to this. So p square, x square, which means that this should be equal to 28. So n times n is n square, and this is going to be minus n. This is equal to 56. N squared minus n minus 56. This is equal to 0. Factorizing this, it is going to be n plus 7. Then n minus 8. This is equal to 0. This gives me n to be equal to minus 7 or n to be equal to 8. Should we be rejecting one of them? Of course, because n is a positive integer and the question has already told me that n is bigger than 0. So we're going to be rejecting this, which means that n is equal to 8. And now I'm going to make use of this. Okay, I'm going to make use of this to find p. So n times p, this is minus 12, which means that p here is going to be equal to minus 12 over n. So it's going to be minus 12 over 8. This gives me p as minus 3 over 2. And the last one is I'm supposed to find q. Q is this entire expression here. n minus 1, n minus 2, p to the power of 3 divided by 6. So it's going to be equal to 8. 8 minus 1 is 7. 8 minus 2 is going to be equal to 6. Then p is minus 3 over 2 to the power of 3 divided by 6. And this will get me q. Q is minus 189. This ends my chapter on binomial, and I will see you in the next chapter.